Good evening, everyone. Welcome to the session 8 of GET Metallurgical Engineering question series. So I will present my screen. Today we will solve 4 questions. Okay. I hope the screen is visible, and we will start with 4 questions. First question is from mechanical metallurgy. So the question is, this is question number 19, GATE Metallurgical Engineering 2012 question paper. The property of a material that cannot be significantly changed by heat treatment is: option A is yield strength, option B is ultimate tensile strength, option C is ductility, and option D is elastic modulus. So what heat treatment does is basically it alters the microstructure. So the properties which are directly dependent on the microstructure are influenced by heat treatment. Now let's look at all the 4 options. First is yield strength. Yield strength. Let us consider a cold rolled material where the yield strength is sigma 1. As this material is work hardened, the yield strength of this material is higher than the normal yield strength. Now what we do to this material is like we anneal it. Okay, now the recovery as well as recrystallization has occurred. Now the material is as received material. Hence, now this will be the tensile curve for the annealed material, where sigma 2 denotes the yield strength of the material. Hence here sigma 1 is greater than sigma 2. Hence by heat treatment such as annealing, we can change the yield strength of the material. Similarly, let's take an example of ultimate tensile strength, UTS. Here let's say we, by a heat treatment, we grow some precipitates inside a material. So what it will do is like the dislocations which are moving plastically, like giving the plastic deformation, will interact with the precipitates, will give you higher work hardening rate. So this N is basically the work hardening exponent. So this N will increase with heat treatment. Let's say I have a material which have finer precipitates, and I have a material which has coarser precipitates. So what this will do is like the dislocations will interact with this, and from finer to coarser we just have to age this. Aging is a type of heat treatment only. Then what will happen, the tau required for this dislocation to go out with the size of precipitate first it will increase and then it will decrease. So this is basically the shear stress required to shear the precipitate, and this is the shear stress which is required to bow the precipitate. So this is the optimum. Hence when optimum is reached, we will reach higher UTS in the material because of higher strengthening in the material than as compared to with finer precipitate or lot much of coarser precipitates. Hence UTS can also be changed. Similarly, as we anneal the material, it imparts recovery and recrystallization. which leads to increase in ductility. Hence, ductility can be also be altered by heat treatment. Now the final question is, the final option is elastic modulus. Elastic modulus is basically a material property. And the slope of this curve in an elastic regime is basically E. So whatever heat treatment you do, it doesn't change. Hence, this property is the only property among the given options which cannot change, which is a material property. The bond strength, it is dependent on the stiffness of the bond, which is dependent on basically the crystal structure. Hence, the option D is the correct answer. This is question number 20, GATE Metallurgical Engineering 2012 question paper. A unit dislocation splits into two partial dislocations. The correct combination of Berger's vector of the partial dislocations for given unit dislocation having a Berger vector a by 2 1 1 bar 0 is. So 4 options are given. So firstly, the given Berger vector, let's consider this as B1, is a by 2 1 1 bar 0. If this Berger vector of a dislocation has to split in two different Berger vectors, so there are basic two conditions which needs to be satisfied. So first is B1 should be equal to B2 plus B3. This is the first condition. And second condition is E1, which is basically the energy of the dislocation with Berger vector B1, should be greater than E2 plus E3. If the overall energy of this dissociation is less than the initial energy, then this reaction will be favorable. So out of 4 options, we have to find which is the option which satisfies both these conditions. Now let's look at the 4 options here. For option A, so we will add these two things. 2 plus 1 is 3, 3a by 6 is 1 by 2. So a I will write in common, a by 2 I will write in common 1, this which is addition of x part, and we will solve for y. Minus 1 minus 2 is minus 3, minus 3 by 6 will be minus 1 by 2. So this will be 1 bar. Now coming to the third, z, 1 plus of minus 1 is 0, 0 by 6 is 0. So this is the basic addition of B2 plus B3, which in turn is the Berger vector here. So first condition is satisfied here. First condition is satisfied. Now coming to the second condition, whether the energy, so energy is basically given by GB square. So I will write GB1 square is equal to, if you square this off, so it will be like 1 square plus 1 square is 2, 2 by 4. So basically it is a square by 2. Now this is for the parent Berger vector dislocation. Now I will write it for GB2 square. This is proportional to a square by 2. So GB2 square plus GB3 square. Now we have to find this. So here if you look, 2 square is 4, 1 square is 1, and 1 square is 1. So it is 6 by 36. So basically it is a square by 6 plus for GB, like 1 square is 1, 2 square is 4, and 1 square is again 1. So 6 divided by 6 square, which is 36, again a square by 6, which is basically a square by 3. So E2 plus E3 is less than E1, which is favoring the dissociation. Hence, favoring the dissociation of B1, which in turn is the correct answer. So the correct option here is answer A. You can try with B, C and D. You won't get this condition to be satisfied. In one case it may satisfy, but the other condition won't be satisfied. So I recommend you to solve for all the three things and then choose this option A. This is question number 40, GATE Metallurgical Engineering 2012 question paper. Arrange the following in terms of increasing severity of quench. P is oil quenching, Q is water quenching, R is water quenching with agitation, and S is brine quenching. So we have to arrange this in increasing order of severity of quench. So let me first introduce you. Like, severity of quench will be directly proportional to the heat extraction rate from the material. So the heat extraction rate depends on the heat transfer coefficient between the steel and the medium in which the steel is kept, and another one is the thermal conductivity of steel. So for all these four cases, let's assume that the thermal conductivity of steel remains constant, which is constant. So it is basically dependent on heat transfer coefficient between steel and medium. So higher the heat transfer coefficient between the steel and medium, more will be the severity of the quench. Now let us look at all the four options. For P is oil quenching. P is oil quenching. Oil quench. So for oil quench, you can see with no agitation, H value is 0.2. Is 0.2. So for Q, which is water quench without agitation, so here poor water quench with no agitation is 1. So this is 1. R is Q with agitation, means basically water quench with agitation. So this is very good water quench with strong agitation, which is 1.5. And S is brine quench. So in brine quench, you can see with no agitation it is 2. So now we have to arrange this PQRS in increasing order. So as you can see that H value of P is the least, then comes the water quench, then comes the water quench with agitation, and finally brine quench. So the most severity of quench is in case of the brine quench. So the correct order will be P less than Q less than R less than S, which is option A. So the correct answer is option A. This is question number 43, GATE Metallurgical Engineering 2012 question paper. Match the phenomena listed in group 1 with the possible mechanisms in group 2. Group 1 consists of fatigue, creep, strain hardening, yield point phenomena. And group 2 mechanisms include grain boundary sliding, slip band extrusion and intrusion, quartile atmosphere, and dislocation interaction. So group 1 should be matched with group 2. So firstly, what happens in fatigue crack nucleation is that, as you can see in this schematic, when the stress reaches a maximum value of a cycle, let's call this as the cycle, fatigue cycle, where this is sigma max and this is sigma mean. So what happens is, like, when sigma max is reached, the dislocation move on this slip planes, and when coming down to the sigma minimum, what happens is, like, slip irreversibility occurs. Like, the dislocation will try to move in a opposite direction, but what will happen is, like, the dislocations won't be able to come back to its initial position. So when sigma max is reached, it is extrusion, whereas sigma mean, when it is reached, it is intrusion. So what happens on the surface is, like, some undulations you will observe, which is basically extrusion and intrusion, and finally the crack will initiate from this notch here, which is generated because of extrusion and intrusion. So the correct answer for P, fatigue, is slip band, extrusion and intrusion. So in creep, what usually happens is, like, so the grain boundary sliding is a basic material deformation mechanisms where grains slide against each other. So as you can see in this schematic, this is the initial microstructure. So what happens if you apply tensile stress to it? So the region here, the atoms are stretched, whereas the atoms here are, like, compressed because of Poissonian contraction. So what happens, these grains get elongated, and this from other side it gets shrink, so because of vacancy and as well as atomic transport. So this gap it needs to fill, because it is, like, thermodynamically it is not favorable to have this much of large gap between the grains. Hence what happens is, like, this grain slides over this grain and closes like this, which is basically termed as the grain boundary sliding. Hence, as this phenomena occurs in creep, it is usually the temperature more than 0.4 of melting point. Here you can see, basically usually it is more than 0.4 of melting, because this grain boundary sliding requires diffusion of vacancies as well as atoms, so that the grain can move from here to here, shift from here to here. Hence it is a high temperature phenomena, which basically is creep when the stress is applied at higher temperature. So for Q it is 1. Now coming to the strain hardening, if you look tensile curve, first is the elastic region, then plasticity begins. So the plasticity, higher the stress required to plastically deform it, more the strengthening, and this strengthening, which is governed by this strain hardening exponent n, is basically dependent on interaction of dislocation with either other dislocations or some precipitates or grain boundaries. So what happens is, like, the dislocation interact with each other, form sessile locks. Let's say if two dislocations interact and they are locked in certain positions, such as jog or kings, let's say. So what will happen, it will again impede the motion of another dislocation flowing or, like, moving on the same plane, which will harden the material more. Hence strain hardening is basically because of moving dislocation, and these moving dislocation interact with each other to form sessile locks, which directly or indirectly hardens the material. So R is 4. And coming to the yield point phenomena, which is basically observed in mild steel because of two atoms. Yield point phenomena. So what happens is, like, if carbon and nitrogen are trapped inside a steel, let's say, let's take an example of mild steel. So what will happen is, like, So the dislocations interact with these solute atoms. So let's say these atoms form a array of like what we say is like, let's say 5 6 atoms are in a single place, so the dislocation will interact with this and get says like it will have more resistance for its movement. So what will happen is like the initial yield stress will be higher, and then it will drop when the dislocation are like away from carbon and nitrogen. Then some serrations will take place, and after that the normal hardening behavior will continue. So this basic phenomena is called as yield point phenomena, and this carbon and nitrogen solute atoms segregating near the dislocations is basically the quaternion atmosphere. Hence, because of this, like because the dislocations cannot move because of this solute atoms, we require higher stress than the actual required stress for the material to deform plastically. And when this solute like this dislocation moves away from the solute atoms, at this point the again stress drops and few serrations come, which are basically like you can say the Luder bands, which are usually formed in a grain, and after that the normal hardening behavior takes place. So for yield point phenomena, the mechanism is quaternion atmosphere, which is caused by the solute atoms and dislocation interaction. So the correct answer is P2Q. I will write it here. P2Q1 R4 and S3 21343. 2143. So the correct option is option C. Amruta, you have any questions?
Hello.
Yeah, Amruta.
Uh, Good evening, sir. I am not a student, sir. I am an NPTEL employee.
Okay,
I
okay.
came here to monitor the session, sir.
Okay, so what is happening is like last week I just changed my timings, slot timing to Sunday, 6 to 7. After that, that was for 1 week only because I wasn't well. From that
Okay.
time, people are not able to join. I guess there is some miscommunication. So I'm just recording the session so that the students can, when I upload it, so that the students can be able to join it.
Okay. For the past 3 days, I mean, not past 3 days, last three classes, no one joined, sir.
Is it for all the sessions?
Not all these sessions, sir. Metallurgy session in particular.
Yeah, because like the strength was like when we started the sessions, the strength was like 5 6 students per class. So
Yes, sir.
what
Yes.
happened is like when we went through the sessions, like few number of students increased, like it went to a 2 digit number, like 10 15 students. Then again it was like more or less like 2 3 students only joining a session.
Yes, sir. I have noticed, sir.
I guess the awareness or the number of students are not increasing. Maybe awareness is required more. I think so.
I'll
If you can
talk in this
transfer, yeah, if you can
regarding.
transfer our thoughts to the committee so that more awareness is there, so that other peoples can also join and benefit from this session.
Yes, sir. Even Ramakrishnan sir was of the opinion that awareness is required, sir, especially for metallurgy.
Yeah, because in metallurgy only 1 2 students sometimes join, or 3 4
Yes,
maximum.
sir. Yes,
Last
sir.
last
Yes.
time no one joined. My slot was on Sunday last week.
Yes,
So
sir. I know, sir. I was there. I came to take attendance as usual, and I saw that no one was there.
and I
Not
thought
not this
that maybe the
every
like
Saturday and
change
Sunday.
of slot is not come like the change of slot is not conveyed properly. That's why I thought that Sunday no one was there. So,
No, sir. Even on Saturday and Thursday, sorry, this Friday and Saturday also no one joined.
oh, no one joined. Okay, okay.
No one. But I heard from somebody that those who used to attend these sessions regularly, they had some exam because of which they couldn't attend,
Oh,
sir.
is it? So,
Yes, sir.
hmm.
Someone said, one of the PMRF scholars said this.
Oh, is it? Because like
Yes.
I used to recall that like for first six sessions, six or seven people were attending it regularly.
Okay, okay.
So for last two sessions only no one has joined.
Yes, sir. Yes, sir.
But I guess some awareness is required so that these guys can join and get benefited out of the sessions.
Yeah, the other PMRF scholars have sent a mail to Ramakrishnan sir in this regard, sir, that
Today,
no
yeah,
one.
yeah, exactly.
Uh,
Today I was supposed to send mail. I was of the thought that maybe some error is there in communication because of Sunday's change of slot. So today also no one joined. That's why I was waiting for today. So I think I would have written mail to him today by today. So I hope
okay,
I guess you can convey these things. I don't have anything to write now.
okay,
You
sir.
just convey it to them so that some steps should be taken on this. Otherwise, we are just wasting our like time and everything.
Yes, sir.
Hmm.
That is true.
So we are like uploading this session so that people can later see these things. I am solving four questions in a session, so but the interaction part is not taken care of.
Yes, sir. I'll escalate this issue to Ramakrishnan, sir.
Yeah, yeah, sure, sure. If
Uh,
possible, you can like again circulate the links and everything. Again, broadcast these things that live sessions are being conducted, if possible.
yes, sir. I'll see what can be done from our end, sir.
Yeah, yeah. Okay
And
then.
okay, sir. Sir, so till when you will be uh, like taking class,
Yeah,
sir? Will you
so
be
this was my eighth session overall. So we are entitled to take 12 sessions total. So
uh,
mostly four more I will take coming Wednesdays.
okay? No, sir. I was asking for today, sir.
Today I guess it is over because the interaction part is not there, hence it is like 20-25 minutes only.
Okay, because I was waiting with the other PMRF scholars till the end of the session, sir, because no one joined, so I was with them.
Ha ha,
So
right.
just let me know when you're like planning to wind up, sir.
Yeah, like the last thing was like I will just summarize the session, that's all. Four questions
Okay,
I have
okay,
already taken, so I will just summarize the session, that's all.
okay, okay, sir.
Okay, then shall I summarize or you will leave?
You summarize, sir. With your permission, I'll leave, sir.
Okay, okay, sure, sure. I will just summarize the session. Yeah,
Okay, okay. Thank you, sir.
yeah. So in today's class, basically we gone through four different questions where first question was depending like what property of a material which cannot be changed by heat treatment. So this is a mechanical metallurgy question. So if you read mechanical metallurgy or watch these videos on NPTEL, you will be able to answer that. It was a simple question. This was a 1 mark question, and in second question, two basic things were required for a Berger vector to dissociate in two different Berger vectors. We have to see whether b1 is equal to b2 or b2 plus b3, and secondly it should be energetically favorable. Basically the gb square of first Berger vector should be greater than gb2 square plus gb3 square. If both the conditions are satisfied, so you have to choose a option where all these conditions are satisfied, and the correct answer was option A. And in fourth, basically this is the knowledge based question. Here I have taken this references from the heat treatments principle and technique book, where you can go through this H values of different media, quenching media, and you can just arrange this on the help of this H values. So you should know, have a rough estimate of this H values, and you can find this in this book, Heat Treatments of Principles and Techniques. And the last question which I took was basically of like the mechanisms which are in fatigue, creep, strain handling and yield point phenomena, which overall I explained you in a simple manner, like how the mechanisms are there in different like in fatigue, creep, strain hardening and yield point phenomena. So the correct option here was like option C. For fatigue, it was slip band extrusion and intrusion, which ideally creates a crack, or it acts as an initiation point for the crack. In creep, as the temperature is usually more than zero point 0.5 of melting point, grain boundary sliding is one of the mechanisms of deformation. And in strain handling, because of dislocation interaction with each other or with precipitates or grain boundaries, strain hardening usually occurs, which we basically see in a stress strain curve. And yield point phenomena is basically occurring because of the carbon and nitrogen atoms interacting with the dislocations. Okay, so I summarize this session like this. So in next session we will have again 4 more questions from GATE Metallurgical Engineering 2012 paper. Okay, thank you.